Welcome to Planet Geo, the podcast where we talk about our amazing planet, how it works, and why it matters to you. Christopher,
hey,
what's up, man?
Not a whole lot. Jesse, I'm so glad that you chose the episode that you chose because you fought me on this.
I know. This is part 2. This is Jesse continuing to, I don't know, what's the phrase that I'm looking for? Eat crow or something like that. I'm not really sure. This is part 2 of our re-releases of some of our favorite episodes going back a couple years now. And this one, Chris, is the Geology of Sand. Only the strong survive, the Geology of Sand. And you came up with this one. I was initially resistant to it for sure. This wasn't like a big blow-up fight. We didn't almost break up over it, but we did have some discussions. And ultimately, you convinced me, and it's an amazing episode. It's opened my eyes to this entire aggregate industry, where limestone crushed aggregate comes from, and this whole entire industry, which we'll have some stuff coming out in the new year on with some interviews with people probably. Yeah, I love this episode, just the societal relevance of geology and why beach sand is not that good, but river sand is great. Things like that. Really, they come down to fundamental geoscience concepts, and they're used in our everyday lives, and we don't even know about it. So this is why I love this episode.
Yeah, me too.
That's all you got to say on it.
That's right.
Sit there and be right.
Well, hey.
You just sit there and be right.
Yeah, I think we should just cut to it, Jess.
All right, before we get to sand, there's a couple ways to support us. First of all, the first link in your show notes is our CampGeo app. There we have visual podcast series. Those are podcasts with some images, some really cool custom gifts to help you understand the basic concepts. The entire intro to geology course is essentially there in audio textbook form, plus some other visual podcast series you can buy. Send us an email, planetgeocast@gmail.com. You can find us on all the social medias at planetgeocast, and visit our website, planetgeocast.com. Let's get to it. Geology of Sand. Hey, so today you kind of brought this to the table. You're like, hey, we should do something on sand. It's really cool. Most people don't pay attention to it. And I must say, Chris, this was a stroke of genius. This is really quite interesting,
Let's not go
actually.
Crazy. No, I think so.
Yeah, so give us the pitch here. Yeah, give us the sales, the elevator pitch for this episode.
Okay, I really struggle with the pitch, though. I don't know, honestly, because I wrote the script for this and this was my idea, like you just said, but I didn't sleep well last night knowing that we were going to record today because I wasn't sure, how are you going to react to this? I didn't know if you'd like it, the idea or not, but then I don't know. I think sand is awesome. I use it a lot in my classes. We have a really long, elaborate lab on sand that takes at least a week.
Well, first of all, this gives us a really interesting insight into the dynamics between you and I, because I do the same thing when I'm writing a script. Oh, is Chris going to like this? Oh, Chris is going to criticize me for this part, this other part. But coming from Michigan, there's sand dunes everywhere in Michigan. So you kind of know sand, right? But most people in the world, I think, they know what sand is. But we as geologists have a very specific definition of sand. And so let's just get that out right away. Let's start with that. And the definition of sand is unconsolidated grains that are greater than 1/16 of a millimeter and less than 2 millimeters. So there's a very narrow, well, it's not super narrow, but a very specific size designation for sand.
That's right. And below that, if it's smaller than 1/16 of a millimeter, we call that silt. And then one step below that, smaller than silt, we call that clay, which is comparable to dust-sized pieces or fragments, okay? Above it, above 2 millimeters, we call that just gravel. I mean, right, is that good enough?
No,
we don't need to get into
is...
the nuances of classifying this stuff.
No.
So we're talking about a grain of sand that fits in between that parameter there. And that's actually quite heavy in terms of the way that sand is moved by running water. Usually then it's too heavy to often be carried in suspension in the middle of the column of water.
That's a really important point, Chris. Sand is a high energy thing. I mean, wind can blow sand, but it can't really pick it up. Like dust, you can have dust storms where dust is carried really high up. Sand doesn't ever make it up that far. when wind blows sand in sand dunes, if you're walking a sand dune, it's a really windy day, you can usually feel sand like hitting you in the foot or the ankle, maybe in your shin, but not much higher, right? Because sand doesn't actually blow up that much higher. It can't carry it. The same goes for water, as you're describing, right?
That's right. Hey, we need to back up though, because we jumped right into it. I don't think we did a good enough job of like, why in the hell are we going to spend this episode talking about sand? I think everybody out there is probably like, what? Really? They're going to talk about sand? Sand is amazing. Like if you look at it under a microscope, the world just blows up. I mean, it's absolutely amazing. And what you can learn about sand, the minerals that are in it, the sorting that it has, the angularity or rounding of the clast or pieces, you can determine a ton about the sand, where it came from, how far it went, what the energy of deposition was. I mean, there's just really a lot that you can do. The whole world just kind of comes alive.
And sand is not one thing. Sand is really diverse. There can be individual mineral grains. They can be quartz or other mineral grains. They can be rock fragments. They can actually be biogenic. They can be clasts of fossils or shells that are in sand. So there are lots of different types of sand out there, and they all tell us something very specific about the geological environment that sand was created and deposited in.
In my intro, in the intro that you gave for me, you talked about my geology class. And so it's a bunch of high school juniors and seniors. And every year we do what is called the sand lab. And I get really excited about it because I think it's cool.
Chris, you get really excited about everything. So, well, this is not a unique.
That's true. I'm not going to deny that. But I have 8 different samples of sand that I've prepared. I put them on these clear plastic dishes. We bust out the microscopes and we look at the sand and I ask like kind of leading questions, right? And they come to conclusions based on what they see and all. It's really neat. But I also ask my students, hey, if you go somewhere, bring me back a bag full of sand. You just need a Ziploc and bring it to me. And we'll write on there with a Sharpie where it came from, who brought it in, the date on it, and so on. I don't know. I probably have over the years, I've collected 250 to 300 different samples of sand from students.
Oh, that's impressive. Wow.
Over the whole world. I mean, I have a student that went to Iraq. He was in the army. And he brought me back a Ziploc full of sand from downtown Baghdad. You know, it's just, it's all over the place.
That's cool.
And so it's really cool. So we use it.
One thing that we just started touching on as we were building this script, and it kind of shocked me, is that sand is really important to society in a way that I had no idea about before this. So this is a massive industry, sand mining and sand uses. And I guess upon reflection, it makes some sense. But as a society, we use 40 pounds of sand per person per day, just in the society.
Okay. Hey, when you first said that, I'm like, no, that prove it. Prove it. Like we delayed our recording so we could talk about this, and we had to verify that is the case. How in the hell, Jesse, are we using that much sand? What are the uses? How's this possible?
Yeah, it's kind of amazing. So that equates to 50 billion tons per year, more or less, and that continues to grow very rapidly because concrete is made up of about 25% sand. So concrete is the main user of sand, actually. And it's actually a very specific type of sand that they're after, the concrete industry. So we'll come back to that, I think, at the end. Michigan, our home state, is the number 3 sand producer in the U.S. And part of that is because there's a lot of sand deposits, but also it's because the auto industry, they use sand for casting metal parts for the auto industry, and it's used in ceramics a lot. It's also used in the fracking industry. So in hydrocarbon fracking, you drill down into a shale that does not allow the oil and natural gas in there to get out because it's impermeable. You frack it, pressurize it, and you create these cracks, but those cracks need to be held open with something so that you inject sand into those cracks to hold it open, and the sand is porous and permeable, allows the hydrocarbons to flow out. So
that's right. It kind of props those cracks open. It's called a proppant. It's like opening a door and the door slams shut. That's what would happen to shale if we just fracked it and didn't use sand. So we got to open the door and put a rock into place to prop the door open, and that's what the sand grains do.
No, that's a great analogy. Yeah, it's a perfect analogy right there. So just to put this into a little bit of context, it takes roughly 18,000 tons of sand to build a mile of highway, which is amazing. 200 tons to build an average single-family house, and this is kind of amazing. So to put that 50 billion tons of sand into context, that equates to 40 pounds of sand per person per day. Unbelievable. 7 billion people, or however many there are now. 40 pounds per person per day is unbelievable. That would be a wall around the planet 27 meters high by 27 meters wide, all the way around the planet.
Oh my gosh.
It's an incredible amount of sand that's being used.
It is. Yeah, so I don't really feel good right now. Seriously, 50 billion tons of sand that we use annually, that's the same amount of greenhouse gases that we put into the atmosphere by mass. Okay, 50 billion tons every single year. Sand is actually the second most important resource behind water. It's the second most used resource behind water.
Yeah, water than sand. That's unbelievable.
Oh my gosh.
Unbelievable.
Yeah. And if you want to go back and listen to our episode on water and like this kind of water crises, we have an episode in season 1 that deals specifically with this, because this is, again, a huge, huge issue that humanity is facing.
And sand is very much the same way. We are facing a crisis here. Much of that sand, much of that 50 billion tons per year is not mined in a sustainable, ethical manner. And so there's a problem, and there's a growing problem, and it needs to be fixed. So it's something that we should all be paying attention to. We're not going to get into that too much anymore, Chris, because you're right. It's a little bit scary and a little bit outside our breadth, because we should talk to some mining experts in sand. That would be very interesting. But we're going to talk about the geology of it and like, how does it form? What are the different types?
Sorry, I want to interject, Jesse. So I'm looking at something here that you actually put in the script, that you said the 50 billion tons that we use a year, most is coming from rivers and inland lakes, and that desert sand and ocean sand is too rounded to be used in concrete or fracking. Why is that? Do you know?
So the desert sand and ocean sand, you can think of this as it's being blown around all the time. So in the desert, that sand is being blown back and forth.
It's too small.
It gets really rounded and it gets made smaller. And the same goes in the ocean. That sand on the beautiful white sandy beaches, that's being washed up and down, up and down, up and down. Whereas a river comes in, it dumps sand during a flood stage, and then that sand just kind of sits there. So it gets transported a little bit, sometimes a long ways, but it doesn't get rounded to the degree that desert sand.
But I don't see what that matters. Who the hell cares whether it's rounded or angular?
I see
how
what
does
you're
that
saying.
affect? That's what I'm asking.
So the surface roughness is really important for like concrete. It's the binding, how well it binds to other stuff. Really round, smooth stuff is not very good at binding, or for fracking, not very great at propping open rock cracks. So you need that roughness to do it. So that's really what we're after.
You need it scuffed up.
Exactly. So sand is really important, as we've highlighted. So let's get into some of the details about the different types of sand, because there's a lot of different sand out there, and it's formed in a bunch of different ways, which means that when we look at the rock record, we can look at a sandstone, and sandstones all can be very different, and we can look at the sandstone, look at the sand, and say what kind of environment existed on Earth when that sand was being deposited. So where do we start, Chris?
One of my favorite things to do when I have students out in the field is to bring like these field microscopes, put them together right out there in the field, and look at sand. And then, all right, what can we determine about this? So not only is sand really, really, really important, it's also very cool. You said, where's it come from, right? Where does sand come from? How does sand form? Sand comes from the chemical and physical weathering of rocks. And then we've talked about this before, chemical and physical weather, and it's been a part of our episodes. We haven't done like a specific episode on that, but we've done it in context, right? What do you think is the most important process in terms of forming sand? Do you think it's the physical weathering or the chemical weathering? What do you think?
I mean, this was a hard one for me. I talked about it before. It's like unclear. I think both are important, because the physical breaks down the rocks, and then the chemical kind of helps to sort them a little bit. So I'm not sure. Which one would you say, Chris?
I would say definitely chemical. And there's a thought process that's involved in this like answer.
Okay.
first of all, what is the most common rock that is continental in origin? What is the rock made of? What's continental crust made of?
Granite.
And granite is loaded with feldspar. Okay. Now, most sand, it's derived from soil. So you get this veneer of soil that forms over the rocks. Okay. And it's being chemically broken down. It's being physically broken down. But the thing is, why did I pick chemical weathering as the most important process? Because what happens to feldspar with chemical weather? What does feldspar turn into?
Feldspar really easily goes to clays.
That's right.
And so it gets broken down. Yeah.
Yeah. So the feldspars actually change into a different mineral and that gets carried away. But what this does, though, is it frees up the quartz that's in the granite.
Mm-hmm.
Okay.
Okay, I see where you're going. Yeah.
Not only did the feldspar change composition and become a different mineral, the quartz now is loosened up, free from its matrix, and now can be moved. Now the physical aspects of it come into play, but it wouldn't have happened that way if it hadn't been for the chemical weathering. That's why I go with chemical weathering being the most dominant process.
That makes complete sense, Chris. And really, you're talking about sort of take a rock, it has a whole bunch of different minerals in it. The chemical weathering wears down a whole bunch of the minerals and leaves some behind. So we're left with this like skeleton. If you took a granite, you just let it chemically erode, really aggressive chemical erosion, the quartz would be the only one that's left. So that's a great analogy. I really like that, Chris. That's a good one. And then this transport, the physical weathering, once it's broken apart and once you have this sort of chemical separation, then the physical weathering takes over. And so it's important to point out that feldspar is breaking down and turning into clays. It's not just feldspar that chemically weathers quickly. Most other minerals in the rock actually do the same thing. Olivines, pyroxenes, amphiboles, micas, most of them will break down and turn into different clay minerals or different other minerals that are lower temperature. And so basically quartz is the only one that doesn't. And so if we look at a sand where we have quartz grains plus other stuff, quartz and feldspar and maybe some amphiboles in there, kind of a dirty sand, what we'd call dirty, quote unquote, what does that tell us about the source of the sand, the rock from where the sand originally was?
So the title of this episode is Sand, Only the Strong Survive, right? And you said it, that quartz, nothing really happens to quartz. Quartz can get broken down into smaller and smaller and smaller pieces, but really it's a very stable mineral, whereas all the other common minerals are not nearly as stable. So if you have a sand that you just described that has a bunch of other stuff in it, it's got some quartz in it, it's got feldspar in it, it's got some hornblende in it, and all these other things, that's an immature sand. In other words, the source of that sand is not very far away.
Absolutely. So that means that there hasn't been enough time. Time is distance here during weathering. So if you have a river that's right at the base of a mountain, and the mountain is all the granite, that river is probably going to have quartz and feldspar and amphibole and stuff in the sand that you grab in the bottom of that river. Now, if that river is like the Mississippi, thousands of miles away from the mountain, it's probably not going to have feldspar and amphibole. It's just going to have quartz for the most part and a bunch of clay minerals in it maybe. But we're talking about sand-sized grains, so the sand is going to be mostly quartz sand. So it tells you how far, because time is distance. Distance equals time for this weathering process. So farther away is more chemically weathered and actually more physically weathered as well, which means that the grains we are looking at will be more rounded. The further they travel, the more rounded they become. And this is really easy to imagine. Think of your sand grain. It's just bouncing along the bottom of the riverbed. Every bounce has the potential to knock off any sharp edges. So more of those bounces means you get more and more rounded, really tiny little beads of quartz when you're really far away from the source. If you're really close to it, there might be more edges to them.
And so those two things together line up to tell you a lot about where the sand came from, right? Rounding, long ways, and the more pure the sand sample is, it doesn't have a lot of other stuff in it, came also from a long ways. So rounding and this kind of, it's sorting, right? I mean, this is a term that, I don't know, I use this term a lot in your, intro
rounding or sorting,
classes, Jesse. Sorting. Yeah.
Sorting. Absolutely. Sorting. Yeah.
Yeah. It's like if I gave you or I gave anyone a jar full of Skittles, which, I love Skittles. It's one of my favorite candies.
Of course you do.
Just love them. They're so good. Anyone, you give them a jar full of Skittles, they sort them out. They know what to do, right? You're going to sort it according to color. 5 different piles, and there you go, right? But that's one way of looking at sorting, is like the different colors equal different minerals, right? So if you have a well-sorted sample, that means it's only going to have mostly one color and maybe a couple of other colors sprinkled in there, right? But if I gave you Skittles that are different sizes and said, now sort these out, again, you know exactly what to do. And so sorting can mean mineral content, and it can also mean mineral grain size or the density of the minerals. They're all going to be deposited in the same kind of environment. So what are you grinning about? You're looking
I'm just picturing you. I can't get over the image I have in my head of Chris Boy sitting on his porch on a hot summer day, just a handful, a jar of Skittles. You got sticky, colorful fingers just chomping away at your Skittles. I'll call you Sticky Fingers Chris from now on. That's a good nickname. So, but it's a
don't call me that. Don't call me that.
Right. Well, it's a really good analogy that this sorting. Yeah, I use sorting all the time in class. I mean, this is a classic, like, sedimentological process that the further away from a source, for the most part, the more weathered and the more rounded these grains sort of get.
And water is really, really good at sorting minerals out, right? It's very discriminating. Glaciers, they don't do that. Glaciers don't care. They don't have to discriminate according to mass or size or all that kind of stuff, but water does. It can only carry what it's capable of carrying.
And we use water in our lab to separate out zircons from quartz and feldspar and all these things. So we use water. It's basically like, we call it a water table. It's, think of gold panning. Gold panning is using water to density sort and size sort. We do the same thing in the lab. Rivers do the same thing naturally.
Question. Most people are familiar with the minerals mica, muscovite and biotite. They're the 2 common ones, right? What do you think? Those minerals, first of all, Jesse, describe what they look like a minute. Then I'm going to ask the question.
Muscovite and mica?
What do they look like, Ken?
Yeah, they're little tiny flakes, very, very, very thin, flat flakes. So actually muscovite, if it's a big piece of muscovite, it's flat and you can peel the layers off. And that small form is very small, flaky, has little shiny edges to it.
If you have ever taken an earth science or geoscience class, you've seen and held probably muscovite and biotite in your hands, and you can't resist the urge to peel them into their thin little sheets, right? My students just destroy it all the time. So would you expect to find muscovite and or biotite in a well-sorted, rounded sample of sand?
No, you would not. And the reason is that behaves very differently in water, right? A rounded quartz grain is going to be bounced along the surface, and it has a certain density to it. Muscovite is actually much less dense, and it has this flat pattern. So it'll kind of float in the breeze a little bit more, if you will, as it's going down the river system. So it could get carried in much lower energy water than a quartz grain can. And so you kind of wash all that stuff off of the quartz, and what's left behind are these quartz grains that are kind of dense and kind of bounce around on the surface. So this is this sorting phenomenon that you end up getting. So Chris, we've been focusing a lot on quartz and really focusing on quartz, which, as you can imagine, makes up really white sandy beaches for the most part. But everybody is probably familiar with black sandy beaches. You see these pictures on Instagram or online, black or green sandy beaches. Those are different minerals. And so how do we generate those types of beaches that have different sand, not quartz sand in them? We have to address that, I think.
So first of all, when you have black sand or green sand, to us, that right away signifies this is mafic in composition. These minerals, whatever's making this stuff up is going to be rich in iron and magnesium. That's what tells us. So whenever you see this, these are usually beaches that are derived in a volcanic setting. But it's not just any kind of volcanism. It's like the mafic kind of Hawaiian type volcanism that I think most people are used to seeing. So, and the reason is because like mafic magma, if you go back to our episode on Bowen's reaction series, these experiments were really designed to explain why certain minerals only occur with other minerals. And really what we're saying is minerals like the really dark colored minerals, olivine, calcium-rich plagioclase, pyroxenes, these minerals, they don't often occur, or they don't occur with quartz. Okay, so if you have mafic magma, you don't have a lot of quartz. So you're not, you can transport this a long ways and you're still not going to get quartz, right? You're going to get something that's reflective of what the parent material was, the protolith.
That's exactly right, Chris. And those beaches, so black sand would be mostly little fragments of basalt or maybe black pyroxenes in there. Green sandy beaches would be mostly olivine, the mineral olivine, where a beach is mostly sand-sized grains of olivine. And the Galapagos Islands, I've been to the Galapagos Islands, and there are some blackish sandy beaches and some greenish ones. There's also these really interesting red ones. And the red ones are basically this dark iron-rich basalt that gets weathered. And so you get little pieces of basalt, but then those get oxidized. So the iron rusts, basically. So you get this dark reddish, blackish sand, which is the basalt. And now remember, there's this little isthmus, like a little peninsula coming off of one of the islands, where one side of this really narrow, it's like, maybe 70 to 80 feet wide beach with a little dune in the middle, right? And it's a couple 100 feet long or something like that. And on one side of the beach, it's black, or this blackish red. The other side of the beach, it's white. And this was really interesting because the reason is because the black side, that's all volcanic pieces of volcanic rocks that form the black. The white side is actually shell fragments. And the reason that they were there was because the wind direction was blowing inland from there. And so it was blowing all the shells and broken down organism bits inland and blowing it up onto the beach, which made this white sandy beach. On the other side, where the wind was blowing offshore mostly, it blew all the shell fragments out into the deep sea. And so it's just a good example of how the beaches really reflect the geology of that area. They can tell you, the wind was blowing, dead creatures back up onto the beach, and on the other side they weren't, and it's all volcanic sand. So these types of sands, a lot of these volcanic sands, black and green, well, they're not common. And the reason they're not common is because this chemical weathering process breaks them down really easily. So one single sand grain on those black beaches will not be around for a long time. It'll get chemically weathered pretty quickly. So they have to be replenished a lot. Whereas a pure quartz sandy beach, that sand grain could be moved up and down around for years and years and years without actually breaking down too much.
It won't break down. You're right. It won't break down. But if the wind direction is wrong, it can take that quartz sand that was deposited and blow it into the lake or into the ocean. And then you're back to square one. If you want the beach, you have to replenish it. But I do want to talk about like Hawaii, for instance. We're talking about an island nation of black rock. So do they have any natural beaches? Natural means not imported sand. How would it be possible to have natural beaches that are more white, more normal looking beaches like what you just described?
Yeah, so these beaches are mostly going to be shell fragments, carbonate, pieces of carbonate. And you could get both old shell fragments and also the carbonate reef parts and sort of chemical deposition of carbonates in these shallow lagoonal settings that get kind of blown up. You can get carbonate mud that gets bigger and bigger grain sizes. So it's either biochemical or chemical deposition of carbonate, and that gets blown up and made into this white sandy beach. So yeah, that's absolutely another way to do this.
That's right. And the other thing is, back in the early part of the 1900s, Hawaii started importing sand, like literally by the shipload, and dropping it off because people are accustomed to white, touristy looking typical beaches, So they have that too, but that's a constant project that needs to be revisited again and again and again through beach nourishment, because the wind blows the sand and the erosion takes it away and off it goes.
So Chris, the other type of sand that we've talked about briefly before was lithic fragments or rock fragments. So this is sand that actually, if you picked it up and looked at it under your field microscope, you'd see that each little grain has a whole bunch of different mineral grains as a part of it. It's actually a miniature rock. So it's a small piece of rock that is made of multiple different minerals. And you see this in places like Japan. In the Japanese beaches, a lot of them are lithic fragments because the volcano is right there. You have a volcano that's making new rock. That rock is broken down. It forms the beaches. You can see this off the coast of Oregon and up in British Columbia as well. And so the thing is these are what we call immature because you're so close to the source rock It's literally, you can see the volcano, and the volcano is being broken down and depositing it, because those lithic fragments, they break down really easily. So it's very easy to take one of those little sand grains, and sometimes you can do it between your fingernails and crush it and break it into the 3 or 4 different mineral grains that make it up.
I could do it between my fingernails, but I don't think you could.
No, you're probably right. I probably couldn't. I've become a little bit of a weakling. Need to get out there in the field and do some smashing of rocks.
Your little professor hands. You can't do that
right.
with your professor hands.
That's right. I stick to my lab work, fixing machines and stuff. It's not nearly as badass as breaking rocks, but they're easy to break down, and so they won't last long. Again, just like olivine beaches or the black beaches, those grains don't last very long, so they're quote unquote immature. And if we take this style of thinking, we're talking about a very modern Earth. Oh, there's the volcano, then there's lithic fragments. Great. How does this carry back into the rock record, Chris? When we look at old rocks, do we see evidence of this same kind of process?
Yeah, one of my favorite places to take students on like an intro to Pierce geology in the field is Pictured Rocks National Lakeshore in the Upper Peninsula of Michigan. It's on the Lake Superior side. One of the cool things about it, in this beautifully layered sandstone, it's got lots of cross bedding in it, lots of sedimentary structures and so on. It has almandine garnet minerals in it, in the sandstone. And that's important because that tells us that the garnet is like you can trace it back to its source. Where did these minerals come from? And they came actually from the Canadian Shield. And so we know the source of where the sediment was coming from, where it was transported, and then where it was deposited. So stuff like that, the mineralogy of old sand that turned into sandstone, can tell us a lot about the geologic history of that area.
Yeah, and Chris, this is something that people do all the time to study ancient sedimentary rocks. So there's quartz a lot in these ancient sandstones. There's also zircon, and zircon is a mineral I'm particularly interested in because it's great for geochronology. We can analyze individual zircon grains. They're very resistant. They're as resistant, if not more resistant, than quartz. And they occur in granites, in intermediate rocks, but they're very small percentages. Like quartz is very abundant, 40% of the rock. Zircon's like far less than 1% of the rock. So little tiny grains, but they get included in these sandstones. And so we can go pick up ancient sandstones, look at the zircons and analyze a whole bunch of the different zircons and tell the age of the crust that was being eroded into the sand that then formed the sandstone. So we can kind of do this sort of tracing like you described with the garnets. We can do this sort of, I don't know what it's called, genetic tracing of the sandstone and say, oh, what was eroding into this basin? And people do this a lot.
That's exactly what I was going to call it. Yeah. And it's important also to note that when you do that, you're dating the age of the grain. You're not dating the formation of that sedimentary rock or when it was deposited as sand. You're going for something else. You're going back to the source material. So,
exactly right. Exactly right.
All right. Well, Jesse, I think we're getting close to wrapping this whole thing up here, but I want to, just for a summary standpoint, sand forms from 3 different broad sources, right? It forms from individual minerals. It can form from lithic rock fragments, and it can also form biogenically, like, calcium carbonate organisms that lived and they died and their shells got blown up onto the beach and that kind of thing. So I want to just use that last one, the biogenic sand, as an example of something that I do in my classes when I have this sand lab. First of all, looking at a biogenic sand underneath a microscope is absolutely amazing. Looking at the diverse colors and the patterns that they have on their shells. And keep in mind too, this is calcium carbonate, which is the same mineral as calcite. So it's pretty soft, right? So biogenic sand is really, really, really smooth and rounded. Okay. The shell fragments, the edges and corners round off a lot with this because of the softness of it. But I have a couple samples from this place that I love in South Carolina. It's called Edisto Island. And 2 sand samples from the same beach. One of the samples has all biogenic, all shells, very little sand in it. And I say sand, I'm talking about grains of quartz in it. It's all shells. Then the other one from the same beach has maybe a 50-50 split, shells and detrital grains, grains of quartz. So this is like, how could this be? This is one of the things that I want my students to like begin to understand. Well, where does the biogenic sand come from? And I'm asking you, like, where would that come from?
So it'll come from the ocean, the organisms in the ocean.
Where would detrital quartz grains come from?
They would come from presumably the mountains nearby or the rivers bringing those from inshore. They're being deposited into the beach from inshore.
They're coming from rivers, right? So how would you have on the same beach then a sample taken, two different locations, one that has no detrital quartz grains in it and one that has a lot of it in it? Like, what kind of conclusion can you make from that?
Well, I would probably say that these are two different times of beach deposition. One where a river, maybe a big flood happened and it deposited a whole bunch of sand into that beach environment and, brought more detrital grains into the system, whereas the biogenic sand was sort of always being deposited there in the background. Would that be a correct assumption, Chris?
Yeah, I'm not talking about a vertical, like, one on top of another. They're two different lateral locations, but you're right. It has to do with proximity to a river, right? The sand that had the quartz grains in it was taken very close to the mouth of a river. Whereas the sand that had no quartz in it, we were just walking along the beach for miles and we were a long ways away from any mouth of a river, any source for that kind of sediment. And so it was just nothing but biogenic sand. So it's like, I don't know. I just love that kind of stuff where you can make conclusions that are pretty simple. They're not very complicated, but they tell a lot.
Yeah, they tell a heck of a lot. That's a great one. And a great way to kind of summarize the variability that you get in sand, even from one beach. And we've talked about how much variability there is in sand around the world in different locations in different geological provinces. And I just kind of want to come back to the importance of sand here and say that, a lot of the mining that we talked about, mining of sand, people were interested in. Industrial uses of sand are interested not in sand from deserts because that's getting blown around and reworked and smoothed out. And again, not in sand from oceans because that's kind of doing the same thing in the beach environment. But rivers move a lot of sand because they're this perfect grain size to be moved by water, bounced along the river in the bottom in normal times, and then carried in a large quantity during a flood. So rivers and lakes are very important for sand given the energy that it requires to move sand a little bit. So sand's important. Sand's interesting. What if this was really fun, Chris? Great idea. It's stroke of genius. I'll say it.
Well,
it was
let's
awesome.
not go that far. I don't know if it was a stroke of genius, but I don't know.
Really fun to talk about. Sand's super important and it tells a lot. Sand's not boring. Just like geoscience,
No.
Rocks are not boring. Sand is amazing.
Well, it's, here's a thought, right? That you take just a simple thing of, hey, let's take a bunch of different sand from a bunch of different places. Let's throw it under a microscope and let's see what we can deduce, right? This is how geologists think. And I think it makes us a little bit different, don't you? Like, we think about things a little bit differently. We have a skill set that I think we have to develop as we live our lives thinking, looking through the world through the lens of a geologist, I don't know. Am I wrong on this?
No, you're right. I've talked to several, employers who end up hiring geoscientists, both in geoscience fields, geoscience adjacent fields, and in different fields like venture capital. And they are of the opinion that geoscientists have a different style of thinking. You're exactly right. It's very observational. It's very data rich. We have to think in 4 dimensions. We think in these huge time scales and huge length scales, but also we have to think about time. We have to think, how does a tectonic plate deform and move? But then how does it do that over millions of years? It's a very visual and sort of complicated 3 or 4 dimensional field. And things that are ultimately underpinned by very simple observations at the end of the day, which makes it really fun. Very, very, very fun. And you get to picture, there's garnet in the sand, and you get to picture like what an ancient sand beach looked like when it was eroding from the Canadian Shield. I mean, really cool. Just amazing stuff. Sand is great. Well, I think that's a wrap, Chris. And you can follow us on all the social medias. We're at Planet Geocast. Send us an email, planetgeocast@gmail.com. Give us a like or subscribe and a review. The reviews in particular really help the algorithm and make us more discoverable. And we really appreciate that.
That's right. We also appreciate it when people share our podcast with people that you think would like it.
Absolutely. Love that. All right. Take care.
Cheers.